Welcome back to the Calculus Analytic Geometry. So I hope you are you are safe and sound at your home and having a good time. So what we will do today is that we will carry on our discussions over the applications of the derivative. So we're going to start what you call chapter number 4 of the book Calculus in Context by James Stewart. So we'll cover most contents from the chapter number 4. Okay, so what we did, let's recall what we did last time. So last time we kind of talked about that how a single idea of derivative can model a great deal of natural and social phenomena. Okay, so the same derivative can model a great deal of what you call a great deal of natural and social sciences phenomena actually. So we'll carry on this discussion. So now what we're going to do in today's discussion, so our task in today's discussion over two things. So the two things are going to be in continuation with what you call the application of derivative. So the topic is continued, applications of derivative. Okay, and the objective is to convince you that the differential calculus gives you a great deal of power to understand and predict the natural and social sciences phenomenon. So what we're going to do in today's discussion, so today's discussion is going to comprise of two parts, hopefully. In the first part, we will talk about related rates. So I'll talk in a moment that what do I mean by related rate, and in the second part I will really start with the introduction to what do you call optimization. So optimization is really one of the area which hugely relies on the techniques of the single variable calculus and multivariable calculus actually. So it depends on both versions of the calculus actually. So we want to do the optimization actually. So let's just start with what you call a first for example topic, what you call the related rates. Now imagine that you are blowing up, imagine to pump in the air into a balloon actually. So what will happen that over the time the size of the balloon will increase actually. So if you have a lesser air here, so it's going to have a lesser size. If it is have, you pump in the more air, you're going to have more size, and you pump in even more air, you're going to have got even more size into it actually. And obviously there is a limit actually, up to which you can pump in the air. So that will be really an optimization problem actually, that okay, how much air maximally, for example, a given balloon, okay, that is made up of certain material can hold inside it actually. Okay, so you pump in air to a balloon, so the balloon gets bigger and bigger and bigger. Now when I'm saying that the balloon is getting bigger and bigger and bigger, basically what I'm saying that there are two basic things which are increasing, for example, inside the balloon. So the one thing is really the volume of the balloon, okay, volume of the balloon. Volume of the balloon, so the volume, so it's like a balloon is occupying more and more place in this space, and also, you know, there are several other things which are, for example, increasing or decreasing as the balloon is getting bigger. So, for example, another quantity is the radius of balloon actually. Now, so let's denote the volume by V and radius by R actually. Now, so these are the two quantities which are changing when the size of the balloon is getting bigger. Now, here is an interesting question actually. If I ask from you that as I am pumping in more and more air, over the time, how the radius of the balloon is increasing actually. Okay, how the radius of balloon is increasing. Now, calculating or measuring the radius of the balloon, for example, from inside is a difficult phenomenon. Okay, is a difficult phenomenon. You think about it, what you need to do to measure what do you call the radius of the balloon actually. But what is easy to measure is what do you call the volume of the balloon, because it's pretty much easy to say that the balloon occupies how much size in the space, within the space actually, it occupies how much space. Okay, so this is easy to calculate, this is easy to measure, okay, while the radius is difficult to measure. While I am interested in what do you call measuring the radius actually of the balloon. So in other words, that as time passes and you pump in more and more air into what do you call into the balloon, how the radius of balloon is increasing. Obviously the radius of balloon is increasing if you are pumping in air actually. But if you are, for example, pumping out air, okay, you don't need to pump actually air. You just need to leave, for example, your balloon away. Leave it alone, and it will just shrink and get to its original position, and hence the radius and the volume would also decrease actually. So when you are pumping in air, the volume of the balloon increases and radius also increases. But I want to know that at what radius, what is the rate at which the radius of the balloon is increasing. Now the trouble is that practically this is difficult to measure, while this is easy to measure. In other words, I can calculate easily, if I can calculate the volume easily for the balloon, okay, but and hence I can calculate what do you call the rate of change in the volume of the balloon over the time. But I want to measure, what do you call this seemingly difficult quantity, what do you call that how the radius of balloon is changing over the time actually. So the trick is this, that in related rates problem, the key trick is, the key step is to know that what is the relationship between the two quantities. So we know that balloon is like a sphere, and the volume of the sphere is what do you call 4/3 pi r cube. So this is what the relationship between what do you call volume and the radius is. And once you have a relationship between volume, for example, and the radius, and the rate at which the volume is changing over the time, then you can easily compute the rate at which the balloon is, the radius of the balloon is changing at the time actually. So the philosophy of such problems is really what? So the philosophy of such problems, related rate problems, is that you will always be dealing with two quantities, say A and B, and one of the quantity is easily measurable through experiments, for example. Okay, so you can measure easily measurable quantity. So it's a kind of a quantity that you can measure easily through experiments. While B is the quantity that you are interested in. Okay, you are interested in. So this is difficult to measure. This is difficult to measure. Now, if you know that how A and B are related with each other through, for example, some formula, and you know that how, for example, A is changing over the time or over the independent variable, then using this information, using this rate of change of easily measurable quantity and this relation, can we compute what do you call the rate of change in the quantity B, which is difficult to measure directly through experiments. So I have two quantities that are related. So if the two quantities are related, their rates would also be related. So there would be a relationship between these two rates as well. And once you have the relationship between these two rates, then using this, okay, using this known rate, okay, using this known rate that you can experimentally measure, and this relation, you can measure this unknown rate actually. You can measure this unknown rate. So in order to solve what do you call the situation or the problems related with what you call related rates, what you need to do, you always have to look for that what two quantities you are talking about, okay, and out of these two quantities, which quantity is, you can measure it experimentally or it is known to you, and what is the relationship between those two quantities. And once you know the relationship between two quantities, and for example, how the one quantity is varying over the time, okay, then you can compute what do you call the rate at which the other quantity, which is difficult to measure, at some rate over the time or over the independent random variable or over the independent quantity. So this is what is really the bigger picture. Now let's just start with, for example, this kind of a problem. Let's just start with this kind of a problem. Let's do such kind of problem and see that what we need to do. So imagine I have a balloon. So this is really what do you call the example one from the related rate part, the section 4.1 of the book. Okay. So what does this question say is that you are pumping the air into the balloon and the size of the balloon is getting bigger and bigger. Okay. Now what you have been given that the volume of, so you experimentally observed, say, that the volume of balloon is increasing at a rate, so the rate of this is giving 100 cubic centimeter per second. Okay, so this is what it is. Now the question is, how fast the radii of balloon is increasing. Balloon is increasing. How fast the radii of the balloon is increasing. Now, in order to solve such problem, there are only what do you call three steps actually. You always, in order to solve such problem, you can take some number of steps to solve such problems. I mean, usually it is thought that when you are trying to solve, for example, some kind of words problem. The words problem are difficult. I mean, word problems seem difficult because you try to do them directly. But if you're going to follow some of these steps, or all of these steps, you will see that it is going to make sense. So the first step is to solve such kind of, say for example, word problem is to create the picture. Try to make picture of the phenomena that has been expressed actually. So I made a picture that I have a balloon, okay, that is what do you call increasing its volume, whose volume is increasing actually, and hence its radius would also increase actually. So here the radius is smaller, the radius is bigger, and the radius is even bigger here. So the first step is to create the picture. The second step is really to give the names to the quantities. Give names to quantities. Okay, so whatever the quantities that are involved in your given situation or given phenomena, just give them name. For example, to volume I give a name V, and to the radius of balloon I give a name R actually. And the third step is that, you know, try to figure out what is the relationship between these two quantities that you have named actually. Okay, so try to find a relation, and by relation I mean equation. Okay, between quantities. Okay, that how the quantities that you have identified are related with each other. And once you know the relationship between what you call the quantities, then you know, try to compute step 4 is you know, you can and then identify that what is given and unknown to you. So in other words, in the given situation, what quantities are unknown to you and what quantities are known to you. Then using the relationship that you have established or that you know between two quantities and identifying and this known information, the given information, combined with what do you call the relation between the equations, a relation between the quantities. Using these two known things, try to compute what you want. Try to compute what is unknown to you. Okay. So this is what this step is. Create a picture, give names to the quantities, try to find a relationship between the quantities. Most of the time this relationship while solving the problem would be given to you, but when you are solving, for example, a practical problem, then you have to establish such kind of a relation actually between the two quantities that you are interested in. And by the way, this is not necessary that these should be two quantities. It could be 3 quantities or 4 quantities actually. And some of them are known to you and some of them are not known to you. And it's not necessary that you're always going to have one equation that relates the quantities. Maybe you can have a system of equations that relates the quantities actually. Okay. So the step 3 is trying to find the relation between the quantities, and step 4 is identify what is given to you, what is known to you, and the step 5 would be do the job. Just do the calculation and try to find what is unknown to you. So for example, in the example 1, what was given to me, that I am pumping the air into a balloon. Okay, I'm pumping the air into a balloon. So I made a picture of it. And once you pump the air into the balloon, the volume and the radius would increase. So the two quantities that I'm interested in are the volume and the radius, and I gave them name. And then, we know that how a volume of a sphere is related with volume of radius of a sphere actually. So this is the relationship. So further, it is also given that the volume of the balloon is increasing at the rate of 1000 cubic centimeter per second. So what we need to find is that how far the radii of the balloon is increasing actually. So this is like 3 steps, and now this piece of information should be translated into the step number 4 actually. So let's do the step number 4. So what is the step number 4 is telling you that over the time the volume is increasing, okay, at the rate what? So the dV by dt is, because this is what it says, the rate in the increase of the volume is this actually. So dV by the volume is changing over the time at this rate. So the rate is always derivative, cubic meter per second. And what we need to find is that what is the derivative, or what is the radius of, and how fast the radius of the balloon is increasing. So in other words, I need to find dr by dt. So this is what that I have to do. And the last and the final step would be that using this information and what is given to you, try to figure out this equation, this quantity that you need to know. So let's do it. So what should we do? So if the V is 4 upon 3 pi r cube, the question is what would be what would be the unknown quantity. By the way, I must add another step here, maybe I should write explicitly step 5, that most of the time using chain rule, compute the unknown rate through known. Okay? So compute the unknown rate through known actually. So this is what that you have to do. So now we are in the step 5. So V depends on R, and V and R both depends on time. So if I want to, for example, compute what do you call dV by dt, okay, so that I can use this value, then I can apply what do you call the chain rule. So if it is dV by dt, so I can write this as dV by dr times dr by dt. This is what it is going to be. Okay? Alright. Now, what would be this quantity? So if I so what is known to me? So okay, or maybe I should do a little bit of more simplification, that dV by dt is going to be what? So if I compute, for example, derivative of v with respect to r, so it's going to be 4 pi r square times dr by dt. So this is the relationship between what you call the rate at which the volume is changing and the rate at which the radius is changing. This is known to me, and I can try to figure out what do you call the radius, what is the radius at this instant, and then using it I can compute what is called dr by dt. So, okay. So another piece of information that is given to me that I ignored previously is that how fast the radii of balloon is increasing when it is given that the diameter of balloon is 50 centimeter. Okay, so given that your balloon has a diameter of 50 centimeter and you know that how the volume is increasing at the rate of 1000 cubic meters per second, 100 cubic meters per second, cubic centimeter per second, then what would be the rate of what do you call rate at which the radii of the balloon is increasing actually. So I have this. Now I need to incorporate this. So the given that the diameter of the balloon, say I call it D, is 50 centimeter, then we know the radius is half of the diameter actually. So it's D by 2, so it's going to be 25 centimeter always. And now using this value of R and the value of dV by dt, I can compute what you call dr by dt. So the dr by dt from this relationship is going to be 1 upon 4 pi r squared dV by dt. Okay, so just throw 4 pi square on the other side, so you're going to get such a relationship. And now you see that you have every single information, you know, to compute what you call dV by dt. So if you substitute all values, so you're going to have 4 times pi, which is 3.14 approximately, times 25 square times 100. So you're going to get what you call the rate at which the balloon is increasing actually, which is around approximately 0.0127 centimeters per second. Okay, centimeters per second. Now we must appreciate this calculation. Now here's the thing. I mean, it's why you know this dr by dt is an interesting quantity, because think about it. You know, computing change in volume is not difficult. Okay, you know, experimentally. So you know, I can, for example, do an experiment. I can pump the air into, say, the balloon at a fixed rate, and then I can say that at that rate the balloon is taking how much time to go from, for example, this size to this size. So in other words, this is going to give me the rate at which the volume is increasing. So calculating or measuring the volume of the balloon is not difficult. But if I say you try to formulate an experiment in which you directly measure the radius of what do you call balloon, you will see, and think for a moment, you will see it's not an easy task to do an experimental setup. Okay, you need maybe a very clever trick to experimentally measure the radius of what do you call the balloon, and how this radius is increasing over the time. Okay, so you must appreciate that mathematics allows us to relate the two rates. Okay, and this is seemingly easy to compute. So using this value, we easily computed what do you call the other rate of increase in radius, which was seemingly difficult to calculate actually. Okay, so that's how the problem should be attempted actually for such kind of questions. So as I said, what are the key steps while solving the related problems? You know, our related rates actually identify the quantities that you are interested in. So the first thing is that try to make a picture of the situation that has been given to you. Then identify the quantities that are related, that are involved in that. What do you call? In that situation, and then try to determine that how these two quantities or three quantities, whatever the quantities are related with each other through some formula, through some equation.